we are going to make a USB2 communication between FPGA and PC using FT2232 in sync mode. In any type of embedded system, we need to have a very reliable and fast communication between our controller or the source, which might be PC, to our hardware. This communication can be done in slower methods using UART, which are previous and older generations, but we can go achieve higher data rates using USB 1, USB 2, USB 3, or even go faster than that using PCIe Express. But it's always good to have a way to communicate with low latency and high throughput between our hardware and PC. This is something that is needed when we are making a software-defined radio, or we want to make a high-speed oscilloscope or a logic analyzer. So this is an attempt to create a full communication. We need to make this tool. We need to create this protocol, how to communicate with the FT2232 IC. We need to have that tool so that we can use it in future developments. So in this video, we first look at what is FT2232 and how we can connect it to the FPGA, and then we look at the Verilog code that is made to configure the FPGA to talk to the FT2232, and then we look at the Python code. So this Python code, because it's done in Python, it's not necessarily running at a very fast pace because, as you know, Python is a very powerful language to use, especially when we want to make a fast prototype. But if you want to get higher USB2 communication speed, we need to go to higher to lower languages such as C++ to achieve higher data rates. We first look at the Python, and we see what is needed to communicate from PC to FT2232. Then once we finalize this, in future videos, we are going to look at the C++ code that help us achieve higher data rates. Before moving on to the hardware, I just wanted to show you the C++ code. You can see the speed got reduced because of the recording we are doing that is taking some of the CPU processing, but the C++ code can help us achieve around 150 megabit per second speed, while the Python code can go maximum up to 8 megabit per second. So this is a very enjoying a series of videos in which we are going to attempt to create this full protocol and try to maximize the speed of the communication between the PC and FPGA, which once done fully, it enables us to create all kinds of different instruments using this fast communication. Either it is a logic analyzer, an oscilloscope, or a software-defined radio, or a controller. So please continue watching us as we create this series of videos and help us to achieve this ambitious project. Let's look at the hardware that I'm using for this project. I'm using an Artix-7 board by Digilent, which is a development board for Artix-7 FPGA, Xilinx Artix-7 FPGA. I think now it's AMD. I'm actually using the A7 35T variant, which is apparently no longer in production, but there are other variations that can be used. Nonetheless, the Verilog code that we have and we are going to develop for this communication can operate on many FPGAs as long as they satisfy the speed requirements that are needed to operate and communicate with FT2232 in sync mode, in FIFO sync mode. We'll talk about that later. So yeah, this is the board by Digilent. One thing that I like from this board is without any special programmer, I just can connect it to the USB and using a Vivado free version, I can uh, send the generated bit file to the FPGA to configure it. So also the schematics of this development board is available, and what I did actually was using the provided file, which also the constraint files, the pinouts of the FPGA are provided here. You can actually just use those to in Vivado without going and looking at the schematic and trying to map the I/O pins. Yes, so that's about the FPGA. The module I'm using is FTDI from FTDI company FT20 to 32H mini module, which is around $30, 30 USD. So one of the things that is that there are some FPGAs that come with uh, physical uh, uh, physical IP that is required to communicate with USB. Um, we call it the PHY level. For instance, the ZineQ FPGAs, they have this already built in the FPGA, and we can use that. But the advantage of using this IC is the flexibility here, because we can connect it to any FPGA as long as it can satisfy the I/O pin speeds. And also there are other advantages, such as we have the access to very low level hardware settings, and also uh, the latency would be definitely lower when we are using this. Um, Additionally, all the USB drivers and DLL files to communicate from the Windows to the IC is available for free, which can be used. We actually um, uh, import these DLL files and libraries to our Python code or to our C++ code, and we can go ahead and use it. So that's why I chose this. And what we are going to do is now see, okay, how we can achieve full USB 2 speed. We are going to see we need to use FIFO mode in the IC, synchronous FIFO mode in this IC, which essentially has 8 bits of data, a clock which is a 60 megahertz clock, plus some handshakes to that are used to for the FPGA to communicate with FT2233 to read or write data. As I mentioned earlier, this is a series of videos in which we are going to implement the communication between FPGA and PC using FT2232. First, in this video, we are going to look at the setup, the wirings. In the next video, we are going to look at the hardware design, how to implement the finite state machine so that the FPGA can communicate to FT2232 correctly. Then we are going to take a look at the Python code to see how to communicate from PC to FT2232. And then uh, we are going to take a look at the C++ code, because in the end, what we need is the C++ code, because it gives us the fastest speed possible. This is a datasheet of FT2232. What I want to show in this datasheet is the pin description and how we need to connect the FT2232 to FPGA in the FIFO sync mode that we are going to use. So I come here, select the pin description, and then I see this table here. This table, I'm interested in the section about the FIFO sync mode, and it shows me what are the pin names and what are the pin numbers that I need to work with the FIFO sync mode. I see here that I need 8 bits of data, which are from AD bus 0 to AD bus 7. The pin numbers are here. Then I need the clock out, which is the clock, because we are using the sync mode. The clock is provided by the FT20 to 32, and it's a 60 megahertz clock. So we have the clock, and these are the handshake signals that we need to correctly read and write to the FIFO. RxF, TXE, RD, WR, SIW, and OE. We are going, in the next video, we are going to see what are these handshake signals, because from the datasheet, we can easily find what is the required finite state machine to communicate to FT2232. But I leave it for the next video. We just now want to wire these pins to the FPGA. Just to make sure that we know the pinouts in the mini module that we use, we need to go and find the datasheet. I downloaded the mini module datasheet as well. You can see there are two pinouts in across this board, and what we are interested in is this CN2 section. If you come down here, there are some power pins, and then those AD signals and AC signals that were required in the table for the data and also handshake of the FIFO, it's easily and clearly mentioned what are the pinouts here. And then what I did was I also downloaded the Artix-7 35T datasheet or the schematic. And basically, from the schematic, I found the pins that are available in the board. And I use those to connect the FT2232 to FPGA. This is, of course, not the best connection, because these are 60 megahertz signals, and definitely this wiring is not optimal. But so far, I was able to make this prototype with them, and eventually, once everything is finalized, the plan is we put all these into one PCB and optimize the wirings. So if I want to show here, this is the mini module, and these are the pinouts, and based on the mapping that I had from these data sheets, I connected all the required pins to the Artix. We are going to see in the next video how the constraint file in the Artix is defined, but basically whatever we connect from this FD22, we just need to keep the track of the mapping, and then in the constraint file in the FPGA, just assign those pins. Here, these are, you'll see in the next video, these are the wirings I used to loop back, because I was showing you originally the sine wave, but also we have the logic analyzer in our hardware, which basically, to test it out, I just created a signal and looped it back to another input, and in the app, I made sure that the signal that I'm reading back is correct or not. So this is the wiring that was done for the setup, and that will conclude this video. In the next video, we are going to take a look at the Verilog code, and then Python, and then the C++ code. And as always, once we finalize this project, we are going to I'm going to upload all the source codes, the Verilog codes, the Python code, and C++ code into the GitHub, so you can download and replicate this. But this, once done, will give us a very useful tool, because now we have a fast communication between our FPGA, which we can design different hardwares in. So we can have the fast communication between that FPGA to the PC. And once we have that, we can use the FPGA and create different types of applications, such as software-defined radio, logic analyzer, and oscilloscope, which we are going to do. Actually, in Atom Pluto, in the ZionQ FPGAs have been used, which have the USB2 PHY in them. But in this way, we are going to create our own communication using FT2232, which gives us the ability, if when we design the software-defined radio, to use many other FPGAs and also have lower latency and more flexibility in the driver and communication. Thanks for watching this video and stay tuned for the next parts.